Hello students, welcome back. The final topic of lesson 11 is 4.8, Gauss theorem on Euler's torsion function. This is what we want to prove. The summation for all positive divisors d dividing n, phi of d, add up to n. So basically, you're getting an identity function. And then here, if you use Möbius inversion, let's see, what's Möbius inversion formula? If you have summation of small f becoming capital F, small f can be retrieved by mu of d and capital F of n over d. But what is capital F? It's an identity function in this case, just n itself. So you're going to get n over d itself, just coming from this Möbius inversion formula. Let me copy and paste so that you can see those in the same viewing window. Alright, in this case, capital F is just identity function. Capital F of n is n. So here, capital F of n over d is, again, identity, so just n over d itself. That's how you get this. So the second line is coming directly from the Möbius inversion formula applied to the first equality. So second is no big deal. We're going to just prove the first. Okay, let's prove it. We're going to do it in two steps. First, we're going to express phi of d in alternative fashion. And then we're going to work out sigma of phi of d. We begin with this decomposition. N is q times d, where q and d are between 0 and n. Yeah, that makes a lot of sense because basically what we want is the sum of all phi of d for all positive divisors of n. So we want n is something times d and something, well, I'm using q for quotient. No problem there. And then we define these two sets out of nowhere. And why do they name A and P, capital A and capital P? I'm not so sure, to tell the truth. There may be something deep behind, or maybe some historical reason, I don't know. Let's just use capital A and capital P. And capital A of Q is the set of all positive integers not exceeding n, where the GCD of K and N is Q. Now, capital P of D is set of all positive integers not exceeding D that are relatively prime to D. So the second one here is something we are quite familiar with. And how many numbers are there? That's easy. Here, phi of D. See, that's by definition, there are phi of D elements here. This one here is a little bit difficult to understand. Now here, let's make a following correspondence from A to P, capital A to capital P, like this. F of K is K over Q. And then we'll prove that this is a one-to-one onto bijection from capital A to capital P. Consequently, they share the same number of elements, and therefore, it's this capital F Q, that's number of elements, and the number of elements of this capital P of D is phi of D. And these two, that's coming directly from the definition of Euler torsion function. The number of positive integers not exceeding D that are relatively prime to D. Now this one is a little bit harder to look at, This one is a little bit harder to see. Number of positive integers not exceeding n that are relative prime, not relative prime, excuse me, that have GCD precisely Q. Interesting. How does that work? Well, you can work out like this. K belongs to A of Q means K is an integer greater than 0, less than or equal to n, and GCD of K and n is Q. And here, we divide everything by Q. K divided by Q consequently n divided by Q, and 0 divided by Q doesn't change anything, but I can certainly consider that as well. But 0 divided by Q is just 0, no problem there. Let's leave it there. Let's leave it there like that. And then again divide by Q, and I forgot this division, sorry about that. Divide by Q and divide by Q, all right. So 0 divided by Q is 0. K divided by Q is, by this definition, it's f of K. And n divided by Q is D. Remember that? And then this GCD computation, K divided by Q is f of K, n divided by Q is D, and Q divided by Q is 1. Ooh, what do you get? We got precisely right here. If you put J as f of K, that's precisely this. So that means f of K belongs to capital P of D, and everything here is if and only if. So we have a one-to-one onto correspondence, one-to-one onto bijection. So thanks to that, capital A and capital P have the same number of elements, and the same number of elements happens to be phi of D. Now, if you're a little bit unsure about this one-to-one onto correspondence, this necessary insufficiency from here to there, let's consider this kind of thing. What do you mean by GCD K and N is Q? K times some X plus N times some Y is Q, right? Okay, here, divide each by Q. K divided by Q, and that you can do because GCD of K and N is Q, so K is divisible by Q. It's an integer, all right. And then N divided by Q, N divided by Q, that's an integer. So what do you get? K divided by P, K over P, K of Q, that was a typo, sorry about that. K over Q, so f of K, yeah, that's the way I define f of K, times some integer x plus n over Q is D times integer y is 1. That's how we get that. From here to there, and eventually there. It works in general too. Yeah, okay, we did a bit tricky computation, but so far we got that. Now using this, let's estimate this summation. GCDs are unique. Therefore, all the integers 1 through n that'll be just all the integers with where q divides n. You see, this is GCD of k and n, so q has to be divisor of n. And for that, if you union them all, then you have to retrieve 1 through n, because whatever 1 through n, if I select whatever integer I select, there will be a certain GCD, which is divisible, which divides n. So there a certain AQ exist. And then those are unique, and those all exist. To take the union them all, then I'm going to get everything back. But then again, GCDs are unique. So no pair of integers have two different GCDs, only one. So if GCD is Q1, then it cannot be Q2. So this union is a disjoint union. So disjoint union, so if you take the number of elements, then this thing is just sum of number of elements, and the left hand side is n. Maybe I should have written this one as n is equal to, and then like this. So that we are taking the number of elements here to the left and becoming n, the number of elements of this and becoming this summation. We're pretty much done. Previously, we proved that the number of elements of AQ is phi of d, right? And we got n is summation of number of elements AQ. So we get the desired conclusion. Summation of phi of d for all positive divisor d that divides n add up to n due to this decomposition and the existence and the uniqueness of the GCD. Well, I have to say this is a difficult proof. I mean, every individual topic that we went through is elementary. I mean, we used GCD, we used computations associated with GCD and so on, and one-to-one to bidirection and things like that. But if you put together, we get something amazingly hard. And that's why this kind of thing is associated to some person out of respect for the person who discovered and proved it. It's called Gauss theorem. But there are so many Gauss theorems out there because Gauss did a lot of things in all fields of mathematics. So you have to call it Gauss theorem on Euler's torsion function. Okay, that completes this lesson 11, and that completes this subtopic in arithmetic functions.